On the screen, we show the insulated cup calorimeter setup with a polystyrene cup in a beaker, a tight lid, a thermometer or temperature probe, and the aim is to measure how variables change the temperature rise during a neutralization reaction between hydrochloric acid and sodium hydroxide. The apparatus panel lists measuring cylinders, a stirring rod, a balance, paper towels, and a data table, because clear equipment and recording keep the test repeatable and professional. We start by pouring a measured volume of hydrochloric acid into the cup and recording the initial temperature after the probe stabilizes because we need a solid baseline for delta T. The independent variable in this run is the volume or concentration of sodium hydroxide solution, while we control the acid volume, the starting temperature, the cup type, the lid, and the stirring, so any change in temperature comes from the variable we changed. Next, you see the sodium hydroxide measured and added quickly to the acid. The lid is replaced immediately, and the mixture is stirred gently so heat is retained and the reaction mixes uniformly. The display trace rises to a peak, and we read the maximum temperature and calculate the temperature change using delta T equals T max minus T initial, which shows the exothermic nature of neutralization. To correct for cooling, we can plot temperature against time and extrapolate the rising curve back to the moment of mixing so the time zero temperature rise is estimated more accurately. We repeat the experiment for several values of the independent variable and include at least 2 repeats at each point, so the mean temperature rise can be plotted with arrow bars. A results graph now appears, with temperature rise on the vertical axis against volume or concentration of sodium hydroxide on the horizontal axis, and the shape shows the temperature rise increasing and then leveling off as one reagent becomes limiting. Using the mass of the solution, approximated by its volume in grams, the specific heat capacity of water, and the measured temperature change, we calculate the energy released with Q equals m times C times delta T, and then determine the molar enthalpy change by dividing by the moles that reacted and adding a negative sign for an exothermic process. Safety and quality panels highlight eye protection, careful handling of corrosive solutions, use of a lid and insulation, consistent stirring and timing, and notes on common errors such as heat loss to the cup, slow probe response, and inaccurate readings. Finally, we interpret the pattern, state that neutralization of a strong acid with a strong base gives a large negative enthalpy change, link the result to particles making new bonds that release energy as heat, and finish by rinsing and drying the apparatus and disposing of solutions according to local guidance.